Honored Custos, honored opponent, dear audience members. Good afternoon, my name is Vladimir, and we are going to talk about multimodal video content understanding. So the talk is going to be organized as follows. First, I will present you to the topic, and then we will dive deeper into the main contributions that I've done with this thesis. So first of all, what is video understanding? Because it might come across as something quite vague to you. Actually, video understanding is some sort of like an umbrella term that includes many subfields, ranging from video classification to video generation. By solving these tasks, we would be able to help with the video editing experience, automate content moderation, or even help visually impaired people to understand what is happening on the videos and help them to have better experience online. Another reason to study video understanding is because the amount of videos that humankind has accumulated so far is colossal. And we would like to use it and train better models. So this is the data from YouTube. Every minute, 500 hours of videos are being uploaded there. So of course, this amount of data is just impossible for like any manual annotation for us. So for this reason, and also we need to consider this as an opportunity for us to train better video models. So this is why it is important to study video understanding. But why multimodal video understanding? Well, because the world is multimodal. When a human watches a video, they rely on both audio and visual cues. There is this famous auditory illusion called McGurk effect that illustrates this point. And I'm going to play this video, and I want you to focus on the mouth of the person who speaks.
Have a look at this. What do you hear?
Ba, 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 ba.
But look what happens when we change the picture.
Ba, 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 ba.
And yet, the sound hasn't changed. In every clip, you are only ever hearing ba with a B.
Humans are also very good at cross-modal tasks, such as imagining missing modality. If I would ask you to give me a textual description of what is happening on the video, you would be able to do it. You would say something, you would write something like the person is speaking in front of a camera, then he shows how to fold and unfold the bicycle. And then finally you see the title screen. And not only that, but also given a visual stream, it's easier for you to imagine how the soundtrack will sound. So what is the scope of this thesis? So first of all, what is a modality? Because in literature, it's often loosely defined. Some consider this as a sensory input, which corresponds to 5 human senses, others as a data type. And in this work, I'm going to use the second definition. And I'm going to focus particularly on vision, text, and audio. As you can guess, a multimodal model is a model that learns from multiple modalities. This is pretty easy. And finally, I'm going to consider cross-modal model as a subset of multimodal models. So with these boundaries, we ended up with the following multimodal video understanding subfields. So my goal in this thesis was to outline each of these topics by providing a comprehensive literature review, as well as to push forward the state of the art of some of them, namely dense video captioning, visually guided sound generation, and audio-visual synchronization. Before diving into those, I would like to briefly and roughly outline the progress in the representation learning. It's all started with the handcrafted features that required domain knowledge. They were task-specific or domain-specific. With the advent of deep learning, we started to train models end-to-end via backpropagation algorithm. And already at that time, we started to see some unification across architectures. Nowadays, however, we don't even need to design the architecture really, because the transformers are general enough to provide us with a good baseline, if not the state of the art. So all you need to do is you can tokenize the text and patchify the image or audio spectrum, and you are set for success. So this thesis was developed in between the deep learning and transformers era. So for this reason, you will see that in all publications, we are going to, the transformer forms the basis of each work that I worked on. So for the rest of the talk, I'm going to cover the major contributions that I did with this thesis. A small disclaimer is that I'm not going to talk about the results too much. We pushed forward the state of the art in each of these publications. So if you are interested in those, please consider taking a look at those or the thesis itself. So let's start with a dense video captioning. First of all, what is video captioning? Given a video, we would like our model to generate a textual description of what is happening on the scene. One may argue that minutes-long video might be, the complexity of it might not, like one sentence cannot cover the complexity of this video, and because the video might contain multiple events. Dense video captioning addresses this as follows. First, we're going to localize important events on the stream, and then we produce a textual description for each of them. In this work, we used 3 input modalities, audio, vision, and speech in the form of a text. That's what goes into our model, along with the previously generated caption words. We have an individual transformer that encodes information from each modality, and later the output of the transformer are fused to produce the next caption word. The results were good, but it was just the first project that I worked on, so it had certain limitations. First of all, there was almost no interactions between modalities. And also, parts of the architecture were redundant. Finally, it relied on a third-party event detector. So we fixed these issues in the next paper. Back then, I was wondering how could we generalize the transformer to tackle multiple modalities and be better at modeling multi-modal interactions. So to this end, I decided to inspired by encoder-decoder attention in the full transformer architecture, I decided to redesign the encoder a little bit. Now it has this extra bimodal attention module, which effectively encodes cues from both audio and visual streams early on in the architecture. The output of this encoder is then passed to the proposal generator that also effectively uses audio and visual cues to produce, to make the localization proposals. So we're going to use these proposals on the next stage, which essentially just streams the input video, and we produce a caption for each of them. So now also notice that I redesigned the decoder, adapted the decoder a little bit to accommodate for bimodal output of the encoder. So with this, we could push the state of the art even even further compared to the previous approach, and also reduce the number of trainable parameters. Now let's talk about visually guided sound generation. The goal here is, given a visual cues or a video, we would like to generate audio which is relevant to these visual cues. And let me start by playing a few generated examples for you. Compared to state of the art, our model was faster, better, and you no longer need to train a single model per class because one model supported them all. How do we achieve this? So instead of modeling raw spectrum pixels, we are going to factorize the problem into 2 stages. First, we are going to make good building blocks, and on the second stage, we're going to pick building blocks and arrange them in a meaningful way given some condition, let's say visual cues or data class. How to make good building blocks? Let's train a spectrogram codebook. This codebook is going to be trained as a part of the autoencoder. This should remind you about vector quantized variation autoencoder. We actually use the variant of VQAE called VQGAN. This is how we train good building blocks. And at this stage, I would like to highlight that it's important to do a good job because it provides us with the upper bound on the performance on the second stage. Once we've done that, on the next stage, we need to learn to arrange the blocks given visual cues. So how do we do that? We extract frame-wise features from the input frames and pass it to the transformer along with the previously generated codebook indices. The ground truth here is going to be the quantized representation of the original spectrogram that corresponds to this video clip. And this is why I said that it's important to do a good job on the first stage because it provides us with a supervision signal for this stage. All right, so we are sampling the codes, but how to actually generate audio that we can listen to. So we start by extracting features from the video that we provided. Then the transformer outputs the first codebook index. And we plug it, append it to the input sequence, and generate the second one. We repeat it autoregressively until the end, which then we can look up the spectrogram codebook and get the quantized representation, which can be decoded with a codebook decoder. Now, spectrogram can be decoded into the waveform, and which we can actually listen to. So that was essentially the idea behind that paper, and we could train a model that generates audios that is relevant to the visual cues for the first time ever for open domain videos. So now, onto the most recent project that I worked on. This is a joint work with Vladimir Shea and Andrew Zisserman from University of Oxford. And this is about audiovisual synchronization with sparse signals. I'm going to start by by defining this problem using the video that I played for BMVC. It's a very short clip, don't worry. And I want you to focus on my face here.
First of all, what is audiovisual synchronization? As you can see and hear, my speech is out of sync. And the audio track is slightly ahead of what you see. Let me fix it now. Now it should be better. This is what we want our model to do for us. In other words, we want to shift audio and visual tracks such that they are aligned.
I said that we're going to synchronize videos with sparse synchronization signals. But what are the dense and sparse synchronization signals? Well, first of all, dense here is not the same dense as in dense video captioning. By dense, here we mean that, let's say, a speech has a dense synchronization signal because it provides you with a continuous signal in time. It's also dense in space because a large portion of what you see gives you the synchronization cues. Now let's consider an example which is both sparse in time and space. In order to synchronize it, the model needs to process the whole video clip because the synchronization cues occur rarely. Also notice that the visual indication of the sound is very small in the frame. As you can imagine, the more sparse is the signal, the more difficult it is to synchronize. And in this work, our focus was on the later case. In this work, we proposed a multi-modal transformer-based architecture that tackles longer input videos. So given audio and visual streams that are potentially out of sync, we start by extracting audio and visual features. And the length of the features grows with things like frame rate or spatial resolution, which should be quite high to do the synchronization properly. Inspired by works like Perceiver and Detter, we suggest having a small set of trainable vectors, let's say 16 of them, that effectively encode useful features via cross-attention modules. We do the same for audio, and the refined feature vectors forms the input to our transformer that now operates on a significantly shorter length. The transformer predicts the offset class, and notice that since we have a lot of the naturally, like freely available videos online, and it often happens that the audio and visual streams are in sync, so we could do this like supervision by artificially offsetting both streams and getting the supervision signals from those. Right, and we can train it with a standard cross-entropy loss because it's we pose it as a classification problem. Since there is a lack of any video datasets with sparse synchronization signals, we curated a subset of VGG sound called VGG sound sparse, which consists of 12 data classes, which, like namely like dog barking, chopping wood, or skateboarding. To conclude, remember that the video data is abundant, it's everywhere around us, and we should consider this as an opportunity to train better models. Remember that the world is multimodal, and this gives us the hint how the model should look like. With the advent of transformers, we were able to use these general architectures to train better models. In this thesis, I showed you two novel ways how other modalities can improve dense video capturing model. Also, I introduced a novel visually guided sound generation model that generates relevant sounds for open domain video clips. Finally, I presented a novel multimodal transformer-based architecture for audio-visual synchronization for videos with sparse signals. If you are interested in learning more about these projects or trying the models yourself for the custom videos that you have, please consider visiting my webpage. We have a reproducible code for all the papers. And with this, I would like to end my talk and thank you all for your attention.